Okay. So this is a section 6.8. We try to find a limit in the form such like limit x approaches a, and here's f of x, g of x. Now, if we are able to plug in a for x into the g and f, if g is not going to be 0, then we can easily get the limit, okay? So that is the case, it's going to be f of a, g of a, in case g of a is not going to be 0, okay? We assume the function continues. But what happens if the denominator, g of a is 0? In that case, we cannot just plug the number, okay? 0 over 0, numerator also 0, denominator 0. We cannot say 0 over 0 equals 1. Anything, okay, if we see a 0 in the denominator, it's not defined, okay? So this is so in case, okay, if one of the following cases happens, if the limit of f of x is going to the limit of f of gx are both equal to 0, and this is called 0 over 0 type, it's not going to be 1, okay? Or if both of the limit are positive infinity or negative infinity, okay? It's going to be plus minus infinity, it's called the infinity of infinity type. Then, okay, then we can find the limit using their derivatives. You can differentiate the function, okay, as long as the limit exists, okay, provided the limit on the right-hand side exists. Okay, the proof is not trivial. This is the proof is not true, but this is a very useful method to find the limit, to simplify the functions. When you differentiate, you simplify the function. Okay, and what we have to be careful is you have to check one of those two conditions. If you otherwise, you will not get the right answer. Okay, you have to make sure that both the limit, numerator, denominator approaches 0 or approaches infinity. Otherwise, you cannot differentiate, continue to differentiate. You have to stop there. Okay. Why this theorem is true? I can give you some idea. Okay, why this is true. Okay, so here's some idea, and then you can see, just believe that, take, and accept this fact. Okay, we assume fa equals g of a equals 0, for example, right? Then f of x, g of x is going to be f of x minus f of a, g of x minus g of a, right? Okay, then by the mean variance theorem, this is going to be f prime as some number, okay? Some number f star. And then this is x minus a. And the g prime here star x minus a. So this x minus a will be canceled out. Yeah, by the mean, we call the mean variance theorem. So that's why you see you have a derivative on the top. The only trouble here is x star, x double star. Those are not necessarily the same number. But this is a number between a and x. So you believe that this is going to be, so it's approaches, you can use the derivatives to find the limit instead of the original function, you see? So that's the idea. Okay, and yeah, so this is the idea we use, okay, to simplify the expressions. Okay, so let's take a look at the following example. Okay, for example, the limit x approaches 0, sine x of x. Now this is a famous limit. Okay, we can prove that this limit is going to be 1 using different method. Okay, but it's clearly it's a 0 over 0 type because sine 0 is 0, x when x is 0, x is 0. So you can apply above formula called L'Hopital's rule. Okay, and then you differentiate sine x to become cosine x, right? Yeah, and that is going to be 1 cosine x. Now you cannot continue to differentiate because the denominator and numerator both do not approach 0. Okay, neither of them approach 0. So you cannot continue that, otherwise you make mistakes. Okay, so you then you here just plug 0 for x, then the answer is 1. Okay, right. So this is we you know that's it's very L'Hopital's rule is very useful method we can use to find the derivative, as you can see, right? Okay, so second example, let's try this natural log of x of x minus 1. First of all, you check that natural log of 1 is going to be 0. And then 1 minus 1 is also 0. You know, it's a 0 over 0 type. You cannot just plug 1 for x into the numerator denominator. You will get 0 over 0, so 0 over 0 is not defined. Okay, you cannot say, oh, that's the same 0. That's why it's going to be 1. No, not that case. Okay, for example, like a 2x over x, both approach 0, but clearly the limit is 2. The top was 2 times 0, the bottom was 2 0, but 2 times 0 you cannot see the 2 there. Okay, because 2 times 0 becomes 0. So okay, so the limit is going to be 2, not 1. Okay. Yeah, we're talking about the limit, not talking about the value. Okay. So limit. Okay. So now you can apply the L'Hopital's rule. You differentiate natural log of x, you get the 1 over x. Then you get here's a 1, right? So you will get, after simplify, just 1 over x. Then you double check, okay, when x approaches 1, and clearly the denominator is 1, so the answer is 1. Okay, it's not going to be, yeah, you cannot differentiate the numerator denominator again, because you have to stop there. Right? All right. Let's continue. Let's have more example. When x approaches 2, there's x cubed minus 8, x minus 2. Now, for this problem, there are several ways to solve it. Okay? By definition, this is actually the derivative of x cubed. When x equals 2. So this is actually going to be x prime 2. Okay, where f of x is just x cubed, right? By definition, right? What is the derivative of f prime 2? Right? So derivative of f prime 2 is going to be f of x minus f of 2 divided by x minus 2. Okay? So if you know that, then you just simply differentiate it to 3x squared, evaluate 2. So 3 times 2 squared is going to be 6. Sorry, 12. Okay? Right? You just differentiate the function. Now, using L'Hopital's law, you can, because it's 0 over 0 type, so it's you differentiate denominator and differentiate the numerator, you get 3x squared. Then you just all need to do is just plug 2 for x, that's you get 12, okay? The derivative of x cubed minus 8 is going to be 3x squared, okay? All right, so let's try another one. You can do it, okay? So it's going to be x squared over 1 minus cosine x. You try this. All right, clearly when x equals 0, the denominator is 1 minus 1. It's going to be 0, and numerator is 0. So you can try to see what you can get, okay? All right, I hope some of you get the answer already. Okay, so that's going to be, first of all, it's checked 0 over 0 type. You put the note to that each step when you move on to using L'Hopital's rule, okay? So it's going to be 2x. When you differentiate that, the derivative of negative cosine x is sine x, okay? So you plug 0 for x in the denominator and numerator, you find that it's still 0 over 0. Then you can continue. Okay, it's 2, and here's cosine x. Then it's 2 cosine 0. It's just 2, okay? So that means when x is sufficient close to 0, x squared is almost equal to 1 minus cosine x. Okay, so that means, okay, let me give some ideas, right? For x close to 0, okay, that means close to 0, then x squared 1 minus cosine x is almost equal to 1, equal to 2. Okay, so I can write something like that. So in other words, cosine x is almost equal to 1 minus half of x squared. So this is a good approximation, a very good approximation from cosine x using polynomials. Okay. And this idea we will continue this idea, to approximate functions later in the next, in the last chapter 11. Now, in the above formula, okay, we only say the limit as x approach a. Actually, this holds for when a is plus minus infinity. Okay, this holds for the case when a equals plus minus infinity. A is not necessarily finite. Okay. Okay. Yeah, it's also, and a could be some number plus minus a, because a to the plus minus can be left side and a limit, right hand side limit. Okay, but let's work on this first. Okay, a is not necessarily be finite. Okay, a could be infinity. Okay, let's try this. 2 to the x and the x squared. All right, so as x approaches infinity, the numerator approaches infinity, the denominator approaches infinity. All right? So you can apply the L'Hopital's rule. It's going to be 2 to the x, derivatives in the natural log 2. And here's 2 to the 2x, right? I already know that limit should be infinite because the numerator grows exponential, denominator just grows polynomial. So, okay, so that then this is against the infinite over infinite type. You can apply, you can differentiate 2 to the x again, and 2 to the x, then natural log 2 square and the 2. Now you have to stop because the denominator is constant, the numerator approaches infinity. So clearly it's going to be infinity, okay? Because only 2 to the x left, okay? Right? And before we do this, we already knew that, right? Exponential, numerator grows exponential is much, much faster than x squared. So the quotient approaches infinity. But you can prove that using L'Hopital's rule. And now how about this? Natural log of x divided by x squared. I think this is going to be 0. The natural log of x grows pretty slow, slower than any polynomial, okay? I can put any, possibly any positive number. Let's say put a here. A is positive, okay? Let's try this, yeah. I believe that natural log of x grows much smaller than, this is my notation, than any power function. Then this is any power function, okay? Yeah, let's use a k instead of a, okay? And then any polynomial function, any exponential function. So whatever who is on the top, okay? The smaller one on the top, then the limit is 0. The larger one is on the top, the limit will be infinity, okay? So here, the smaller one, natural log is on the x to the positive power, okay? But this is a 0, this is an infinite over infinite type, so you can apply the L'Hopital's rule, right? The derivative of natural log of x is going to be 1 over x, and this will be k, x to the k minus 1. So let's simplify it first, okay? When you simplify, you will get x, move 1 over x down here, so you get x to the power k. And clearly, the denominator approaches infinity, so the numerator is constant, that's why it's going to be 0. Okay. Right? Let's try a slight different type of problem. It's not necessary to be the single function. You have x minus sine x, and x minus tangent x. All right. First of all, you check that it's 0 over 0 type because when you plug 0 for x, you get 0 over 0. Okay. So you can apply the L'Hopital's rule. Right? Differentiate. Differentiate the numerator, you will get 1 minus cosine x. Differential denominator, 1 minus, what is derivative tangent x? It's secant square x. Okay? So, so what is my next step? When x approaches 0. I like, I can do the following. Okay, let me simplify it because I don't want to differentiate secant x. If I differentiate secant, you can try that. It's going to be 0 over 0 type again because secant 0 is going to be 1. Yeah, if you don't do any simplification, and then you can continue to differentiate. Okay, it's negative to sine x. And here, what is the derivative of secant square x, right? What is the derivative of secant square x? That is going to be derivative, right? It's negative 2 secant x. Then you have to differentiate. So derivative of secant x, right? So derivative of secant x is going to be tangent x, secant x, I think, right? Because secant x is 1 over cosine x. When you differentiate, you will get, yeah, sine x over cosine square x, yeah. So, okay, then you have to simplify. I think you have to simplify, otherwise it's getting more and more complicated, okay, when you differentiate, okay? So it's better to simplify secant tangent x over, sine x, right, minus 2. This is 1 over cosine x. If you want to put, yeah, secant square x, so it's cosine square. Then it's sine x over cosine x. I think after you simplify it, you will get nothing in the denominator. Sine x sines canceled out, it's cosine cube x. Then you cannot apply the L'Hopital's rule here. So you just plug 0 for x, you get cosine cube of 0 divided by negative 2, so it's negative 1/2. But why not at the very beginning here, simplify it? It's even much quicker, okay? So let's try this, okay? I don't like secant x, okay? I don't like secant x. So I get 1 minus cosine square x, okay? Then how do I simplify? Okay. Well, we can do that, right? So 1 minus cosine x, and this will be cosine square x minus 1, and then there is a cosine square x here, right? Combine those two together, right? So you move this cosine square x to the side, right? You will get 1 minus cosine x, but cosine square x minus 1 can be written as cosine x, cosine x plus 1, and here cosine square x. All right, so 1 minus cosine x minus 1, which we cancel out, you get a negative 1. So after you simplify it, you get a negative cosine square x and cosine x plus 1. Now you cannot simplify further. But if you plug 0 for the numerator denominator, you will not get 0 over 0, right? Instead, you will get negative cosine square 0 and cosine 0 plus 1, so it's negative 1/2 because cosine 0 is 1. So you study, trigonometric functions in Math 154, okay? Even you got C or B over there after you practice, here in calculus course. Okay, if you retake that test, you probably can do much better. Okay, this explains why we have to you have to get a bachelor degree in mathematics or math education in order to teach high school. Even you only get the B or C in high school math. Okay, then you still can become high school teacher after you get a degree because you continue practice, you improve. Okay, at the end you know everything. Okay, so you find out that's easy, teach high school. Okay, it's not necessary, a majority of probably you don't need must have a grade of A in high school math in order to teach high school, as long as you get a bachelor degree in mathematics and math education. Yeah. Okay. Of course, you have to love teaching. Okay. Right. So now let's take a look at the next problem. Okay, so natural log of square x divided by x cubed. How do you find the limit of this? Well, first of all, you see when x approaches infinity, natural log of square x approaches infinity. So it's the infinity of infinity type. But when you come to apply the L'Hopital's rule to this problem, you have to differentiate numerator and denominator. I think you have to modify it first, because it's really not a good idea to differentiate natural log of square x directly. So you should express, otherwise you have to use a chain rule, right? So if you express in this form, then it's much easier. So let's differentiate the numerator and denominator. The numerator is 1 of x, denominator is 3x squared. Then you have to simplify before you continue to differentiate. It's going to be 1 over 6x cubed, right? X times x squared is x cubed. Okay. So now you cannot use you cannot apply the L'Hopital's rule here, because the numerator is constant, denominator approaches infinity. It's constant over infinite time. It's not infinite over infinite time. So, but clearly this must be 0, because the denominator is getting larger, larger. The numerator is constant. It's obvious. Okay. Right, so let's continue. Yeah, we'll just do some exercise here. It's nothing new, just only one L'Hopital's rule how to apply them, okay? But just be careful. Don't just continue to differentiate. If you differentiate the numerator and denominator, okay, and even you get the same answer, but you still wrong, because you cannot differentiate. If you differentiate numerator, it's 0, and differentiate denominator is going to be 18 times x squared, blah, blah, blah. You know, the limit is still 0, right? But that's incorrect. Solution, okay, answer and the solution is different, okay? Solution contains all the steps plus the answer, okay? Let me repeat again. Okay, so on the test, on the quizzes, you have to show your solutions. Answer is just one number or one expression. And this can be a multiple choice problem, for example, just enter number. If you take it Mobius later on, I'm still working on that. You know, I have given you some extra assignments. Then you just needed to enter one answer. Okay, if answer is wrong, no credits. I don't care how did you do it. Okay, so it's a different kind of test. So you have to show this. You know, if even you get a right answer and the middle of the step is wrong, and you don't deserve the credits, full credits, only get a partial credits if some idea is correct. Okay. So you have to learn how to express it clearly as much as possible. Okay. Now some students just say, I know this guy, just put a 0 there. Well, if you just put a 0 there, you still have to explain why you come up with 0. Right? Or you copy from someone, you know, right? So you have to show the work. I will not give you full credits if you just say put a 0 here, then that show nothing. Okay. If it's 10 problems, 10 point. If it is 10-point problem, a maximum I'll give you 5 points. Right? Without any explanation. Okay. So let's try, okay? So this is it's not even quotient, right? It's just product of two functions. So you have to modify this function. You get x cubed and ex squared, okay? Then clearly it's going to be infinite over infinite type. And it's also clear then, it is clear to me, this is a limit is going to be 0. Why? Because the numerator grows polynomial, and the denominator grows much faster than exponential, because the e to the x squared there. It's not just e to the x, right? So yeah, you can at least you have to say something like that in order to jump to a conclusion. Without saying anything, I cannot give you full credit. But what I really want you to do here, I want you to apply L'Hopital's rule. Okay, you get 3x squared, and e to the x squared will be e to the x squared. When you differentiate, you get 2x. Okay. Then you simplified. I get 3, here's x, and e to the x squared, and it's 2, right? And then this is still infinite over infinite type. So let's differentiate the 3, and here's 2 times 2 is 4, e to the x squared and x, okay? Yeah, differentiate the denominator, you get 4 e to the x squared and x. All right, so now it's clear, right? It's clear it's going to be 0, okay? Some still maybe write 3 over infinity over, that's going to be 0. That makes sense, okay? But 0, infinity over infinity does not mean equal to 0 or 1, okay? All right. So sometimes the function, just a product, you have to change it to the quotient in order to apply L'Hopital's rule, okay? L'Hopital's rule. Okay. For example, here's another interesting. It's a product also. X times x sine pi of x, okay? I just put the 1 here. I don't need that, 2 or 3 doesn't matter, okay? So just x sine. I never see this, right? It's a product. It is a product two functions, right? And the x approaches infinity. Okay, how to do that? It's not easy to see because this is actually going to be infinity times 0 type. So infinity times 0 type, it can be changed to, you can change it to 0 over 0 type, okay? Because you can move infinity to the denominator, right? So right, 1 over 1 of x is just x, so that's right. Okay, then it's become quotient. Now what are you going to do? Then you can apply L'Hopital's rule to solve the problem. Okay, you can differentiate the numerator and denominator, right? Because it's a 0 over 0 type, right? 1 of x approaches 0, sine 1 of x approaches sine 0. It's 0. Okay. All right, when you differentiate the numerator, the denominator is going to be negative 1 of x squared. When you differentiate sine 1 of x, it will be cosine 1 of x times negative 1 of x squared. All right, not too bad. Those two actually cancel out, right? So this is just the limit as x approach infinity is cosine 1 of x, so that should be cosine 0. That's just 1. Okay. All right, our next problem is to find the limit as x approaches positive infinity, 1 of x minus 1 over sine x. Wow. This is not going to be, this is just a difference. It's not even a product, right? This is looks like a infinity minus infinity type. Right. It's undetermined. You cannot just say infinity minus infinity is going to be 0. If you want to apply L'Hopital's rule, you have to express as a quotient. You can try, right? Maybe the limit is 0. Maybe the limit is 1. Maybe the limit is 2. There's a gap between 1 of x and 1 of psi x. We don't know yet, right? So we try to express as a quotient. So it's going to be sine x minus x and x times sine x. Great. Now it's a quotient, it looks like. But so if we plug 0 for x, see, L'Hopital's law still holds for side limit, okay? I have to say that for the side limit. X approaches 0 from infinity. It's okay, yeah. So this is going to be 0 over 0 type. Okay, let's see. I wanted to try first, okay, to see if we're able to get a limit. Okay. Yeah, give me a break. Yeah, I'm waiting for you. Okay, I give you half a minute, okay? All right, so let's apply the L'Hopital's law here. A differential numerator is again cosine x minus 1, right? The denominator product rule, okay, sine x plus x cosine x, right? Then double check, is it going to be 0 over 0 type? Yes, because cosine 0 minus 1 zeros. And then you plug 0 for x, everything, every term is 0, so 0 over 0 type. I can continue apply the L'Hopital's law. When I differentiate, I get a negative sine x only, right? Good. Negative sine x. And this will be cosine x. Good. And here will be cosine x minus x sine x. Yeah, the product rule for the second. Okay. All right. It's not too bad. It's going to be 0 over 0 type? No. The numerator is going to be 0. The denominator is going to be 2. So the answer is going to be negative 0, 2 minus 0. So it's 0. All right. So sine x minus x approaches 0 fast than sine x times sine x. Sounds like that, right? Yeah, the gap is getting smaller and smaller. There's no big gap. And let's double check, right? Yeah, I think so. This is our answer. The next problem, how about x minus sine x? Wow. Then what are we going to do? I can't even combine that. Right? Any clue? Is this the infinite over infinite type? Right? You cannot apply L'Hopital's law here directly. But it cannot express as a quotient. Maybe. But I think the answer is going to be positive infinity. The reason is natural log of x grows much smaller than x, and right, much smaller than a to the x. A is positive, greater than 1, right? So the gap between natural x and x should be getting larger. That's just said, common sense, right? So the gap is getting larger, and then the limit should be equal to infinity. Now, how to make an argument, more accurate argument, to say the limit is going to be infinity? Okay, how do you do that? Okay, we modify this x minus natural log x. I take x out. It's 1 minus natural log of x divided by x. Okay, so now it's clear. This part approaches 0. We already did that, right? So this whole part approaches 1. And the first part approaches infinity. So there's the product of two functions. The first factor approaches infinity, second factor approaches a positive number. Then the product approaches positive infinity, I think, as x approaches positive infinity. Clear? I think this argument is pretty clear, right? Right? Yeah, using the fact. Now, only thing you can have to prove that if it's not a fact is going to be natural log x over x is going to be 0, okay? But now our next problem, it's getting more and more strange functions, okay? X to the 1 of x. But what kind of function it is? It's not product, it's not difference, right? But we still want to get them in quotient. So this is going to be the x approaches infinity. 1 of x approaches 0. So it's like infinity to 0 times. They're all stringent type. If infinity is square, then it should be square. But infinity to 0, it's not going to be 1. So I needed to modify this function. I need to modify this function. Right? Yeah, you think about it, okay? I still give you time to think about it. Any ideas? So here's a typical trick. It's e to the natural log 1 of x, okay? Right? You make it more complicated, looks like, right? Actually, you simplify the problem. Right? It's going to be e, and then this can move down here. So it's 1 of x, right? Natural log of 1 of x is going to be natural log of x divided by x. And I think that this one has a limit. We already know that. This is going to be e to the 0, okay, which is 1. Okay, using the fact, okay, natural log of x approaches infinity, and natural log x of x should be equal to 0, okay? Yeah, you have to state that fact. here, we already did that. And you can approve that using L'Hopital's rule. We're okay now. And using the same idea, you can find the limit. And here's x to the e to the x, okay? I don't know what is the limit. It's harder to tell right now, this moment. All right. Probably still the limit is 1. Okay. Now let's try. It's e to the natural log of x to e to the negative x, right? And this will be, you move this term to the right-hand side, and actually you can put it into the denominator. Okay. So this one approaches 0, clearly. So that's why it's going to e to the 0, which is 1. Now using the fact, okay, using this fact, the limit is going to be 0. Why? You can apply the L'Hopital's law again to this. So it's 1 e to the x, right, by L'Hopital's rule. And that's clearly 0, right? All right. Let's do more. Let's look at some strange function. Yeah, you have to practice on those problems. Otherwise, you have no clue what you're going to do. Something like that, right? And you look at this, what type of function you're going to get. When x approaches negative infinity, the first factor is negative infinity, right? Then second natural log of 1 over x approaches 0. So it's actually natural log of 1. It's going to be 0. So infinity 0 times 0 type. So you have, you cannot jump to the conclusion right away. How to deal with this? Yeah. All right, think about that, okay? I'll give you half a minute to think about it. Right, half a minute, more than half. So we have to convert it to a quotient. The only thing we can, only part we can make a change is x. So I moved it to the denominator. Okay, it becomes 1 of x. Then it becomes 0 of 0 type. Then you can apply loop this. Okay. Now you can change the variable. There's something you prefer to change the variable, or you can keep it, continue to differentiate. Okay. Yeah. If you don't want to change the variable, then just differentiate, and this is going to be 1 of x squared. When you differentiate, it's negative 1 of x squared, right? And then this, when you differentiate, is 1 minus 1 of x, and times the derivative of negative 1 of x. That's going to be 1 of x squared. Okay. Then you simplify it. Okay. So what you get here, you will get negative. So it's 1 over 1 minus, right? What is that? That is left. And when x approaches infinity, and this term approaches 0, right? This approaches 0, negative infinity. So it's going to be, the answer will be negative 1. Right? That's it. Now, if you change the variable, you can let u to be 1 of x. Then when x approaches negative infinity, 1 of x is negative, approaches 0, so it's 0 from negative side, okay? And then here is going to be natural log of 1 minus u and u. So the derivative becomes much easier. Still, it's, you can apply the L'Hopital's law because it's 0 of 0 type. So you will get 1 and differentiate that to 1 negative, right? You end up with the same result. Okay, it's going to be negative, right? Negative 1 over minus u. It's going to be clearly it's negative 1 over. It's negative. Okay. All right. Another problem. All right. So here's a problem, right? When x approaches 1, it looks like the infinite type minus infinite type here, right? You can assume x approaches 1 from positive side. So how can I do that? Well, just combine them to get a quotient. And the x natural of x minus 1. Then you will see what type of the function you're going to get, right? Then you get when x equals 1. This is 0 type, of 0 type, okay? So you can apply, look at this rule. Right, apply L'Hopital's rule. Differentiate x times 1 of x is natural of x plus x times natural of derivative natural is just 1 minus 1. Okay, the product here and plus x minus 1 of x. Okay, and before we continue, we should simplify. The numerator is just equal to natural of x, right? X over x is 1, so cancel out. The denominator is this. What do we get? I think it's also 0. That's a 0. So it's a 0 over 0 type. You can apply L'Hopital's law here. Now, there are a couple ways to do it. Either you modify this again. You don't want to see x minus 1 of x, right? Then you bring x to the top. Okay, so you can You can write like x natural x, x natural x plus x minus 1. Okay? Yeah, then there's no fraction in the denominator. And this is still 0 over 0 type. So let's differentiate, okay? When you differentiate, you get natural x plus x times 1 over x. It's product rule. And here's x plus x times 1 over x. And this is just 1. I think now you can, now you get natural x plus 1. Here's natural x plus 1 plus 1 plus 2. So this time it's not going to be 0 over 0 type. Actually, it's going to be 0 plus 1, 0 plus 2. It's 1 half. Right? Yeah, just plug plug 1 for x. Natural log of 1 is 0. We did a lot of exercise, yeah, right? Let's get some more from the book. So here's a question. X approaches infinity. 1 minus x to the 1 of x. Okay? I should, no, I shouldn't write it this way. It's x approaches 0, not infinity. X approaches 0. Be careful, yeah. X approaches 0. So what type of function? It's like a 0, 1 to the infinite type. Okay, it's a strange type. Okay, so you can, what you do is use the e natural log 1 minus x to the 1 of x, right? Then you move this number to the his side. Okay, and you will get natural log of 1 minus x over x. And here's e. So what is that limit when x approaches 0? So you have to, yeah, my conclusion is this is going to be 1. Okay, so this is going to be 1. Okay, why? Let's take a look at. Okay, this is a 0 over 0 type. So you can apply the L'Hopital's rule. You get 1, and then get 1 minus x, and you get negative 1. Okay? So we don't know, right? It actually turns out to be negative 1. Okay? It's going to be negative 1. So this is negative 1. Okay. Yeah. Yeah, you can write down the answer, then you show me how to get this part, in the last part. It's why then it's going to be negative. So it's e to the negative. Okay. All right. Next problem is very similar. 1 plus 1 of x to the power x. Okay, let's try this. Okay, using the same method. Try to solve this using the same method. Okay. So is e to the natural log of x here, and x, right? And then you move x to the side, and you get x, right? Then I have to find the limit of this. Okay, so let's try this. Hold on. I already forgot this one on X. Okay. All right, and in order to find this limit, you change it to the quotient. Now, I think we did this problem before. The limit is going to be 1. You can change the parameter if you want. Okay, make it easier to the computation. So you can let u to be 1 of x. So when x approaches infinity, u approaches 0 from positive side. Okay, so u in h log of 1 plus 3. It's much easier, right? No quotient. All right, so this is a 0 over 0 type. So you can apply the L'Hopital's rule again, and clearly the answer is 1, okay? So the answer is 1, then what do we got? We got the following important identity. E equals the limit as x approaching infinity, 1 plus 1 of x to the x. Okay? This is how do we approximate the number e. Okay. This is where the e from, okay? It's going to be, yeah. This is an important identity, okay? In particular, when n approaches infinity, 1 plus 1 of n to the power n is going to be e, right? X approaching infinity, n approaching is the same here, okay? So e can be approximated by this. Okay, now if you invest some money, okay, in an account, whatever, okay, some fixed rate, let's call CD making it, because CD is always a fixed interest rate, okay? Let's say some money, okay, initial deposit, okay, at annual interest rate of %, okay? Then depends on how the interest is compound this whole 1 year. You can divide the whole year into n parts, equal parts, right? It can be n could be 12. If it's quarterly, n equals 4, right? So we can assume that compound n times per year, okay? So let's find the formula after t years, okay? What is the balance? So initial deposit, okay? At the end of the first period, okay, it's going to be 1 plus I is going to be interest rate, right? We can I have to convert to the percentage. So yeah. So like 3%, right? It's going to be R over 100. Okay. Yeah, if I is already written in the decimal form, then you don't need to divide by 100, okay? If it's 2%, then like 0.02. Okay, and divide by n, right? So this is the first, at the end of the first period. Could be at the end of the first month, end of quarter. But t years means how many periods, right? T times n. That's at the end of the t years. This is a balance, okay? Okay, now, if a computer can does, we can compound it continuously. Compound continuously means compound every second, every, n can be very large, okay? And the annual interest rate is fixed. So if if the interest is, if it is compounded continuously, okay, that means P is going to be the limit as n approaches infinity. Okay. Then what do you get? You will get the limit. You have to deal with this limit, right? Okay. And I think we are able to find the formula right now. I'm going to rewrite this. And here I'm going to put 100 n divided by r, okay? And yeah, because this is going to be 1 over n, right? Okay, so n is already used. So 100 n and the t. Okay, this is a constant fixed. After cancel out, it's just nt. Okay, there's no n, yeah, just t. Oh, r. Okay, r. Okay, now we already did that. This limit is going to be e. Okay, it's p0 e and rt over 100. Okay, so that means the balance after t years, if it can compound continuously, it grows exponentially at the rate of r over 100. If it's 3%, this will be 0.03 times t. Okay, so that is this is a way, why we have to study this type of limits. Okay, we already defined the limit here. This limit. Okay, the limit as n approaches infinity, 1 plus r over 100n times 100n divided by r. That's going to be e. Okay, you can change the variable. R over 1. This can be just x, right? Yeah. Right. This whole number, it can be denoted by x. Okay, this whole number can be denoted by x. So this is going to be limit as x approaches infinity, 1 over 1 minus x. Okay, x here is going to be 100n over r. Okay, so that's why you get e. Okay, anyway, so if for the interest, if you're given the annual interest rate, and if it's compounded continuously, means almost every second, the computer can do that. Bank will not do that. Okay, bank usually say monthly. At the end of each month, you get the interest. Because sometimes do the annual. Okay, then you will get this formula. It's exponential growth. So that means if you are willing, okay, if you are willing to put the $1, $10 in an account, and if it's a fixed interest rate, like maybe 3%, like CDs, and you can estimate how big a number you're going to get in 100 years. Of course, you will not exist, but you can say this. You can give this money to your grandson, okay? But actually, the purchase power of that money probably is almost the same like right now. Why? $10 only can buy bigger pizza, for example. Why? Because the inflation rate is also about 3%. Okay, so you're not going to beat the inflation rate. Okay, so after you get $1 million that time, okay, oops, I can only buy one pizza. Okay, so of course that time the US dollars, they cannot continues put more zero there. They will divide by 100. So $1 million maybe just converted to $100 or $10. Okay. So eventually you are going to get a $1,000 bill and maybe $10,000 bill. Okay. Probably can see that date. Okay. And I remember I went to Romania one time and I got money on the paper. I cannot even read it. How many zeros there? Oh my God, I became millionaire immediately at the airport. Okay, but it's in Romania money. Okay, so that is crazy, right? Okay, so exponential growth is pretty fast at at the end. Okay. So this is yeah, we're talking about growth rate here. Coming back to the growth rate, we studied that last week. Exponential growth. Okay. So anything, any place you put the money there, if the interest rate is fixed, it's only 2 or 3%, and you are not going to increase the value of the money. Okay, because the inflation rate on average in the United States is 3%. I believe that. So you're not going to beat the inflation rate. Okay, so about 7% every 10 years, the number will be doubled. So that means if you put the $100, 10 years later, you get $200. But this $200 purchase power is not like doubled. Probably only 60% of the, yeah, 160% of the original purchase power. Okay. So it's pretty complicated. So this major is called actual science. If you are good in math, you can think about actual science. Actual science is one of the top major, top professional jobs in the United States.